A'udhu Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. Welcome to the second lecture of the third week. So we were discussing chapter number 4, that is imperfection in solids, as per your course plan. So we'll start with a brief summary of the previous lecture and then we'll move to the new topic. So in the last lecture we discussed the basic introduction, what the imperfections are, and we discussed that the existence of a perfect crystal is a highly ideal thing, and you won't find any crystalline solid without the defect in its crystal structure. That is why it is really important to study about the imperfection in solids, and there are various kinds of imperfections exist in the crystalline material, and defects are generally considered to be something unwanted, but that's not the case with the crystalline material. Instead, we intentionally produce defects in our crystalline materials to fashion specific characteristics as per our requirements. So you pointed out there are four major kinds of the defects in the crystalline structure. The first one, the point defect or zero-dimensional linear defects, planar, and the body defect. In the point defect, there were two major types of the point defect. The first one, the vacancy, and the second one is the self-interstitial. Vacancy was simply the absence of an atom from its lattice site, where normally the atom exists, while the self-interstitial was the presence of an extra atom from the same material in the interstitial spaces where the atom normally doesn't exist in the crystal structure. Then we discussed a special kind of the point defect, that was the impurities in solid. Impurities in solid, we also discussed that the existence of a pure material isn't simply possible. There always be impurities in it, and we most of the time add impurities to get certain properties into our material. And one of the common example for that one is an alloy, and we discuss some more generalized terms, that is the solid solution. While discussing the solid solutioning, we discuss when any foreign atom comes into the crystalline material, either of the two cases occur. Either that foreign atom that comes into the crystal structure, it reacts with the local material and form a new crystalline structure, that is known as the intermetallic compound. It forms a compound in a specific proportion. Another name for that one is ceramic material. Or that impure atom that comes into the crystalline structure of the host material, solvent material, it doesn't react with it, instead it's form a mixture, and it occupies spaces within the crystal structure without disturbing the original crystalline structure. And common example for that one was steel, which is the solid solution or an alloy of iron and the carbon. In the solid solution, we discuss there are two kinds of the solid solution, either the substitutional one or the interstitial one. The substitutional one, in this particular case, the diagram you are seeing, was the chromium in the case of stainless steel, where the chromium atom comes into the crystal structure of iron and simply replaces iron from its original atomic site. While in the case of interstitial solid solution, the foreign atom, where in this case is the carbon, it comes in the crystal structure and occupies the interstitial spaces. It doesn't replaces the host atom, instead it occupies the interstitial spaces. So in the solid solution, the foreign atom is called as the solute atoms, while the host atom is called as the solvent atom. And another name for that one we discussed was the matrix and the reinforcements in certain cases. Then we discuss a few rules that helps us to understand the degree to which the solid solution will form. There are certain factors that helps in increasing the possibility or increasing the degree to which the solid solution will form, and they altogether is known as the Humer-Rothery rules. So in the case of the substitution solid solution, we discussed there's a factor of atomic radius between the solid and the solvent atom. It shouldn't be greater than 15%. There's a crystal structure, they both should have the similar crystal structure, electronegativity. There shouldn't be greater difference between them, otherwise they will react with each other. Or the valency of the solute atom must be greater than the solid one to support the solid solutioning. And in the end we discuss some what the interstitial sites really are, and we draw the octahedral interstitial site in the FCC lattice and the FCC unit cell, and we solve a problem 4.5 of your textbook. Now after that we will jump to our today's lecture. So in today's lecture we will discuss the second type of the defect, that is a linear defect or the one-dimensional defect. So what the linear or the one-dimensional defects are? They are also known as the dislocations. Dislocation is a linear or one-dimensional defect around which some of the atoms are misaligned, or in other words you can say some of the atoms are dislocated from their positions. If we discuss in detail, this is a concept that was introduced in 1934 by a few researchers. It is a defect responsible for the phenomena called slip, by which most of the plastic deformation occurs. So a plastic deformation is a permanent deformation in the material, and that is caused by a phenomena called slip, and that slip is caused by the dislocations, right? Dislocation motion produce plastic deformation of crystal at a stress level well below the shear strength of the perfect crystal. So let's suppose if we have a crystal, perfect crystal of iron, and it has certain amount of shear strength, the maximum shear stress that it can bear, the shear strength of that iron crystal. So if a dislocation is present in that crystal, then this material might fail at stresses well below the shear strength, just because of the presence of the dislocation or by the dislocation motion. While discussing this topic, we will be time and again using three different terms. The first one, dislocation, we will be using dislocation motion, and the slip. So you should have some clarity about these three terms. Dislocation is a noun, it's a defect, it's a thing that is present in the crystal structure. Okay, dislocation itself is a thing that is present in the crystal structure. While in the previous case, like the point defect, there was a defect present in the crystal structure and there was nothing else. But in the case of the dislocation is a defect, is a thing present in the crystal structure, but it also moves. So there's a phenomena called the dislocation motion, and that dislocation motion is called a slip, right? And they causes the plastic deformation, the permanent deformation in the material. Now moving ahead, in the absence of obstacles, a dislocation can move easily on the application of a small force. So if there are no obstacles to the dislocation in the crystal structure, dislocation can easily move. If you have a perfect crystal, that's well and good. But if the dislocation are present, then that material will fail at a stress level well below its original strength. But if we add the obstacles in the way of the dislocation, then dislocation will have a hard time in moving or in causing the plastic deformation, in causing the permanent deformation in the material. So there is a perfect crystal, and there is a crystal with dislocation, and there is a crystal with dislocation as well as the obstacles to the dislocation. So there are three different things. There is a perfect crystal, there is a crystal with the dislocation, a defect in it, and there is a crystal with the defect of dislocation as well as obstacle to that defect, obstacle to the motion of that defect, right? But if those obstacles are absent, then dislocation can easily fail the material at the smaller forces. So dislocation not only important for explaining slip, so it is not only important for understanding the slip, why the plastic deformation is occurring, but dislocation is also connected to many other mechanical phenomena such as strain hardening. If you have studied the stress strain curve in some subjects, or you will study in chapter number 6 in this subject, so you will see what the strain hardening is. So dislocation is somehow connected to this one, and the yield strength, yield point, fatigue, creep, and the brittle fracture. So they all are somehow connected to dislocations. So if we move on, what slip actually is, what the dislocation motion actually is. So the process by which plastic deformation is produced by dislocation motion is termed as a slip. So that process in which a material is deformed just because of the motion of that dislocation, that defect, that is called as a slip. The crystallographic plane along which the dislocation line transfers is called a slip plane. You will see what it is. So that dislocation motion doesn't occur in every plane in the crystal structure. It tends to occur in certain planes. In the unit cell there are a lot of planes, so dislocation motion doesn't occur in every plane. It occurs in certain plane, that is known as a slip plane. So slip occurs when the shear stresses exceeded the critical value, so the atoms move the integral number of atomic distances along the slip plane. What does it mean? If we are applying the stresses on a crystal structure, so there is a shear developed in the system, in the crystal structure, and when that shear exceeds the critical value of that material, so the dislocation or the slip moves the integral number of atomic distances along the slip plane. Let's suppose this whole plane is our slip plane, this whole is a slip plane, and dislocation is moving from this left towards the right. So these are atomic distances from 1 to 2. This is the one atomic distance. This is the second atomic distance we have, then the third atomic distance, then the fourth one. So these are the integral multiple atomic number, or the integral number of atomic distances, right? When we observe the surface with a microscope, so when the such surface which has undergone the dislocation motion, which has some slip in it, it is observed under the microscope, a step shows up as a line called a slip line. So you can see when such surfaces are observed under the microscope, so there is a step kind of profile you will observe, and it is shown observed as a line that's called a slip line, along which a slip occur. And there are many terms that are new for you, and you will have a good idea when we start discussing the types of dislocation. Okay, so just bear with us and we will have some clarity about it. Now, as we discussed earlier, there are certain crystallographic planes and direction in which movement of dislocation is easy, and they are known as a slip system. So we discuss here that there are certain planes called a slip plane where the dislocation moves. So such crystallographic planes, as well as there are certain direction in those planes in which dislocation motion is easy, they are altogether termed as a slip systems. So what the slip system really are? Dislocation do not move with the same degree of ease along the all crystallographic planes. As we discussed earlier, there are many crystallographic planes. Let's suppose this is the FCC structure, and we have a one plane like this. This is also a plane, the front face, you can see this is also a plane, right? So we have many planes in FCC structure. This is just for an example. So but dislocation do not move with the same degree of ease along all the crystallographic planes. It doesn't mean it has a lot of planes, then the dislocation will move along all the planes. It won't move along the planes, along all the planes, rather it will move along certain planes with ease. So there are some preferred planes in direction for slip to occur, called as slip planes and slip direction. So those planes in which dislocation moves easily, they are called as slip planes, and within those planes there are particular directions. So you see, even we have the slip planes, within that slip planes the dislocation doesn't move along all the direction. Within that slip plane, dislocation move along particular directions, and those directions are termed as the slip directions. Slip system in general depends on crystal structure and that the presence of atomic distortion is minimum. So how to identify the slip system? Let's suppose you have any BCC structure or the FCC structure. How to identify the slip system? It depends upon the what kind of crystal structure we have, and also depend upon atomic distortion that are already present in the structure. Maybe we have crystalline structure but it has a lot of point defects, so it will also alter the presence of slip planes. Maybe our plane changes according to the presence of defects. For a particular crystal structure, slip plane is a plane which has the highest planar density. Now what the slip planes really are? Those planes in the crystal structure which has the highest planar density, or they are the most dense atomic packing. They have the most dense atomic packing factor. So in the crystal structure, slip planes are those we have the highest planar density, or they are most dense atomic packing. And same is the case for the slip directions. Within those highest planar density planes, slip direction are those directions which have the highest linear density, and you have studied this planar and the linear density in chapter number 3, and we discuss just briefly in our previous lecture as well. So how to identify, we'll just check out for the case of FCC system. So slip system and FCC structure like this one. In FCC, the 111 plane family are most closely packed planes. So this is a 111 plane you can see here, and all the family of it one. What is it, the family? All the possible combination of 111, including the negative 111 and including the integral multiple. So we have the 111 plane, or we have the -1 plane, or we have the 1 plane. All the family of planes that are included in this one, they are the most closely packed planes, or the highest density planes in the FCC structure. And in these planes, slip occur along the direction family, this direction family, the 110. And you know, if this is the family, then it includes all the direction that have the possible combination of 110. So we have 110 included in the same family, -110 is also belong to the same family, 220 also belong to the same family, and all the possible combination and their integral multiple. So we have the 111 plane here like this one, right? So we can have the dislocation along this line. Just let me just change the color. So there are multiple directions in this plane. We can have the dislocation along this one, this direction as well. We can have the dislocation along this direction as well, right? We can have the dislocation along this direction as well, right? But we won't have the dislocation along this direction. Why is that so? Although it is within this 111 plane, it is within this 111 plane, but this direction is less dense. It has only 1 and this 2. It has only 2 atoms along this line, while this direction has 3 atoms, 1, 2 and 3, 1, 2 and 3, and 1, 2 and 3. So they are the more dense, they have the more dense linear density, or they are the most dense direction compared to this one, or same the case with this one. They have only 2 atoms along these directions. So the slip system, it is a system along which the slip moves, along which the dislocation moves, and a slip system comprises of the slip planes or the slip directions. So within any crystal structure, slip planes are the most highly dense planes, and within those slip planes, the slip direction are those which have the highest linear density. So I hope it's clear now. Now dislocation are of 3 types. The first one, edge dislocation. The second one is screw dislocation, and the third one, the combination of both edge and screw, that is called as the mixed dislocation. So we start with the edge dislocation first. In edge dislocation, in this type of dislocation, An extra half plane exists in the crystal structure, and the edge of which terminates within the crystal structure. So what happens here? There's a presence of an extra half plane like this. This one, as you can see here. This one, as you can see here, an extra half plane exists in the crystal structure. So just because of this, it's an edge of it is within the crystal structure. So its edge that is within this screen, you can see if you project it backwards within the screen here. So its edge is within the crystal structure. The line at the edge of an extra half plane is termed as a dislocation line. So this edge that is passing through all these atoms into the screen, that is called as a dislocation line, or that is called as dislocation itself, the edge dislocation itself, or the dislocation line. Now, before moving ahead to these points, we'll just discuss a vector that is known as a Berger vector. So what the Berger vector is, as a vector, you know what the vector is. Vector is something which tells the magnitude and the direction. So Berger vector represents the magnitude and the direction of distortion by dislocation. So whatever the distortion produced by the dislocation, Berger vector represents its magnitude and the direction. So for edge dislocation, Berger vector is perpendicular to the dislocation line. So for we have the dislocation line here into the screen, and our Berger vector is in this direction. So Berger vector is perpendicular to the dislocation line, and we will see in a moment how it is perpendicular to the dislocation line. In the chapter number 3, you must have studied that the crystal structure is highly symmetric, means it appears to be same. A perfect crystal structure I am talking about is highly symmetric. It's appear to be same in all the direction. Even if you tilt it at any angle, it appears to be same from all the directions and all the angles. So if we have a perfect crystal structure, let's suppose I'm just considering this part of the crystal as a complete crystal. So we start from here. A Berger vector is a closed loop thing. It's a closed loop vector. So we start from this point, we'll move 2 units up, 1, 2, we'll move 2 units towards the right. Just before that, just define a convention here, that is we will be moving from right hand and start to finish. Sorry for this one because I'm using my mouse. I don't have any pen right now. So we'll moving from right hand side and from starting to finish. So from this point we started, we move 2 units up, then 2 units toward the right, 2 units bottom, and 2 units toward the left, right? So we have the closed loop now, and it shows our crystal structure in this region is perfect. There's no impurity in that one, or at least there's no distortion here. It is in a perfect condition here. So if you draw it around the dislocation, so you can start from here. Starting point was this one, so we'll move from right towards the left. So this is our starting point, our end point should be here. So 1, 2, 2 units towards left, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So you can see here we still have an open loop here, and this is the indication there are some dislocation in this region, or our crystal structure is not symmetric in this region. And how much is the magnitude of this one? So we'll start from starting point towards the end point. So I'll make like this one. We'll make from the starting point towards the, this is our Berger vector for this dislocation. So, and its magnitude is 1 atomic distance here, right? So, and if you observe this crystal structure, within the region around the edge dislocation is a localized lattice distortion. So because of this presence of extra half plane, there is some distortion in the lattice structure, in the lattice. The atom in the upper part with the extra half plane are under compression, So the upper part of this lattice, which has an extra half plane, the atoms here are under the compression because we have the same amount of the volume and there are some extra atom in it. You can take an assumption of a bag and you put some extra book inside your bag, so your rest of the books will be under compression, whereas atom below are under the tension to fill up the vacant space. While there is some vacant space here, so these atoms are in tension, they are moving towards the vacant space to fill the space, while the atom in between, they are under the pure shear. You can see here, you can see they are under the shear stress. So atom in between are under the shear, and this effect of squeezing into the vacant space, it fades away, or the effect of compression or effect of this shear, it fade away as you move away from the dislocation. And so the away you are from this dislocation, the effect of this compression tension fades away. So there is a region of lattice distortion. It's not like the whole lattice is distorted. There is a region of distortion that experiences this compression tension and the shear. So if we move ahead, how this particularly edge dislocation moves, how the slip of the edge dislocation occurs. So in edge dislocation, half plane moves in response to the shear stress produced in the direction perpendicular to the dislocation line. So we discussed this is our dislocation line. First of all, we should remind that the edge dislocation is represented by the symbol like this one, right? So edge dislocation is represented by the symbol this. So in edge dislocation, half plane moves in response to the shear stress produced in a direction perpendicular to a dislocation line. So if this is our dislocation line, and these are the stresses being applied, the shear loading being applied, and that is perpendicular to the dislocation line, as you can see here. And when these stresses exceed the critical value, the extra half plane at A, this one, is forced to the right, and this in turn pushes the top half plane of B, C and D. So when this half plane is pushed towards the right, it pushes the top halves of the planes B, C and D further towards the right. And if the stress are sufficient enough, so the bond of this B breaks with its lower half and it makes a bond with the upper half of the A. Now the A becomes a complete half plane, while the upper part of the B becomes a new half plane. Now A becomes a complete plane while the upper part of the B becomes a new half plane, and in this way it keeps on moving towards the right, and the process is repeated until the extra half plane is emerged from the other end surface, and this keeps on repeating until it emerges from the other end surface, forming an edge that is in 1 atomic distance wide. You can see that was equals to our Berger vector, which was telling the magnitude of this dislocation. And if we observe this edge dislocation under the microscope, you can see here this image was taken by Enke et al. While they were conducting research on phase behavior of colloidal silica rods. It was published in Further Discussions in 2013. So they observe this layers of atoms here, and if you closely observe this one, you will find half planes here. Let's suppose this one, this is the line of atoms that is moving. There's another line of atoms that is moving here, but there's an extra half plane. You can see here this one. Same the case if you see here, there are multiple extra half planes. So this is the one plane of atoms that is moving this way. There's another plane of atom that is moving this way, but there's one half plane, there's another half plane here, right? and it gives rise to another phenomena which we will discuss in this lecture ahead. So this is how it looks like under the microscope. Now moving towards the second type of the dislocation, that is called a screw dislocation. So unlike the edge dislocation, which has an extra half plane in it, in this type of dislocation the lattice itself shares so the part of that lattice is offset due to shear. What does it mean? In the edge dislocation, the part that was sharing, that was offsetting towards the other end, if you see it again, in the edge dislocation the part that was offsetting was an extra half plane. It was something extra. But in this case of screw dislocation, there is nothing extra that is offsetting, but the lattice itself is shearing because of the shear stresses. So it's under the pure shear, and it gets its name on why it is called a screw dislocation, because the type of the motion it undergoes. Let's suppose if the stress is being applied here like this one, so if you see, if we draw a Berger vector around this one, 1 2 1 2 3 4 1 2 3 4 1 2 3 4 and 1 2 again. So there's a opening here, there's an open loop here that shows there's a dislocation out of symmetric lattice. So what is a Berger vector here? We can draw it like this one. We can draw from start towards the end. This is the direction of that Berger vector, and this is the magnitude 1 atomic distance. So how come it is called a screw dislocation? If we see here, let's erase all of this. So it moves like this one step. If there's another further stress applied, it will move like further downwards, that will move like further downwards. So it keep on moving like this one. That's why it's called a screw dislocation. The dislocation is linear and it extends into the lattice. It's a linear type of dislocation and it extends into the lattice. The plane of atoms has been sheared, it has been completely sheared, so the top half of the volume along that plane is sheared. We will discuss what it actually is. In the case of the edge dislocation we discussed, the Berger vector was perpendicular to the dislocation line. The Berger vector was perpendicular to the dislocation line. If you see here again, this Berger vector was perpendicular to dislocation. This was the dislocation within the screen. While in the case of the screw dislocation, the Berger vector is parallel to the dislocation or the dislocation line itself. How is that so? So the plane that is undergoing the shear is this one. This is a plane that is undergoing the shear, is it? And this is our dislocation line. Let's draw with this one. This is our dislocation line, and the symbol for the screw dislocation is okay. This is a symbol for the screw dislocation, and for the edge one was this one. So how come the Berger vector is parallel to this one? As we draw the Berger vector there, if you move here from 2 atomic distance, then 1 2 3 4, then 1 2 3 4, then 1 2 3 4, 1 2. So the Berger vector that was drawn here, just change the color, it is parallel to this plane we just draw, this red one, right? is parallel to this plane, and so as it is parallel to this dislocation line. So that is why in the screw dislocation the Berger vector is parallel to the dislocation line, and this is how it moves. If we keep on applying the stresses here like this one, so it moves one atomic distance at a time. It moves one atomic distance at a time until we have a complete line that is moved one atomic distance towards the right, and we have a new edge on this side emerged from this side. I'll just show you some image for this one that you have a clear idea. So when the extra half plane was moving towards this edge, it emerged from this edge like this one. So we have some extra volume here. This is an extra, and this depth was an atomic distance that was equal to an atomic distance, like we previously saw here. That was an atomic distance here. So same is the case in the case of screw dislocation. There is no half plane although, but this whole structure, the upper part of this whole lattice move towards this one. So ultimately what we have here will be this complete, what we'll have here like this one. So this is our, it's not visible, this is our Berger vector, and we have again a half volume of the lower upper half of the this cube, this lattice has been pushed towards the right. So we have this extra half area here, right? And that's the width of this one is equal to one atomic distance, or the Berger vector for this one. So I hope it's clear now. Moving towards the third type of the dislocation, that is a mixed dislocation. Although it has nothing new, it is just a combination of screw dislocation as well as the edge dislocation. The present, it has some extra half plane inside its crystal lattice that is also being offset towards the extreme edge, and also it is being subjected to the shear stress, and so the whole lattice is being offset towards the other end. So this one is called as a mixed dislocation, and that is mostly in the practical case. Now we'll move towards the second type of the third type of the defect, that is the planar defects. That is also called as the two-dimensional defects. So the third type of defects is the interfacial defect. Interfacial or the planar defects are two-dimensional defects. The first one was the point defect, that was the zero-dimensional. Then we discuss linear defect, the one-dimensional. Now we are moving towards the two-dimensional defects. They are called as the interfacial or the planar defects, and they are normally separate regions of the material. Within the material, they are separate regions that have either the different crystal structure or they have the different crystallographic orientation. So they both are possibilities. So means in the same material we have different planar defects that have either the different crystal structure or the different crystallographic orientation. So starting with the first defect, we have four different types: the external defect, grain boundary defect, twin boundary defect, and this twin boundaries is you can say a sub part of the grain boundary. It is linked to that one, and we have some miscellaneous defect. So starting with the external surface defect. External surface of a crystalline material itself is considered as a defect. So if you have any crystalline material, and just making upper surface of it, it has atoms on its surface here, so that is considered itself as a defect. Why is that so? The crystal structure terminates here. Obviously we have the crystal structure here, but there are no crystal structure beyond this limit because it's an external surface. Owing to this, atoms at the external surface are not bonded to the maximum nearest neighbors. So although atoms here they must be bonded to the maximum nearest neighbor, but the atoms at the surface they are not bonded to the maximum nearest neighbor atoms. So this is why these atoms are in high energy state. So these atoms are in high energy state compared to the atoms deep inside the lattice here. And this is the case, they readily reacts with the impurities because of less number of satisfied bond, because they have the high energy surface energy and they have the less bonded so they are more ready to react with the impurities in the atmosphere. So that itself is considered as the defect, and besides there are some other factors as well. The second one is called as grain boundary defect. Grain boundary defect. In previous discussion we have been discussing several defects in this chapter, like the point defect or even the dislocation. They were about the perfect crystal or the single crystal, you can say. We have been discussing about the dislocation or the defects in the single crystal, but in reality we have almost all of the materials are polycrystalline material, except if we make something in a controlled environment for specific purposes. So grain boundaries have a great influence on the plastic deformation behavior of a polycrystalline material. Although all the defects have influence on the plastic deformation behavior of the crystalline materials, but for the case of the polycrystalline, grain boundaries exert great influence on that. Besides, there are other factors that affect the deformation behavior. But before going into the grain boundaries, we will just recall what is the difference between unit cell, crystal, and the grain. Unit cell, you have discussed, you have studied, it's a basic building block of the crystalline material. And when those unit cells are translated along XY axis, XYZ axis, it makes up the crystal lattice, right? Sorry. Like if we have this one, we have XYZ axis, and we may have a lot of unit cells here over each other that are arranged in a perfect order along XYZ axis, so that all together makes up a crystal. Right, so we can just translate an unit cell along XYZ axis, so they all together, the aggregate of the same unit cell is termed as the crystal. Now what the grains are: grain is a region in the polycrystalline material where the unit cell and the crystallographic orientation remain same. So in the polycrystalline material, the grain is that region where not only the unit cell is same, like the crystal has the same unit cell, but it also has the same orientation. The crystallographic orientation of that crystal is also the same. Then we will call that to be the single grain. Otherwise, if the structure is same, the crystal structure is same, but the orientation is different, we will say that to be the another grain. That's another grain, right? So if you observe it under the microscope, and even you can observe it without the microscope as well. If you guys have seen any sheet of steel or the aluminum that is not coated with the paint or any other anti-rust chemicals, and you observe it under the sunlight or any other light source, you will see some shiny patches over its surface, and those shiny patches over its surface are basically the grains that are visible microscopically. And you can even observe it in the electric poles. If they are not painted or coated with any other chemicals, you can observe on the electric poles as well. So this is the image taken of the aluminum sheet under the microscope. So these different patches are actually the different grains in the crystal structure, and there's a possibility that the grain here, it also has a BCC structure. Let's suppose, just an assumption, it also has the BCC structure like this. Okay, and there are a lot of BCC cells in this grain, hundreds and thousands of BCC cells. And the grain here, the dark one, it also has the BCC structure. But there's a chance that the orientation of that BCC structure is different. Although they both are BCC structure, but one is facing this side and other is facing the other side. That grain is facing the other side. Although they both are BCC structure, but the light source of the microscope, it is being reflected more by this grain compared to this grain. So we can observe, although they might be same crystals, but their orientation is different. So we have two different grains in the same material, and they both are aluminum, and they both might be same structure, either BCC, FCC, HCP or any other, but their orientation is different. That is confirmed. So I hope it's clear what is the difference between unit cell, crystal and the grain. And if you see the types of the grain boundaries, now there's certain other points about the grain boundary as well. The case of the grain boundary is somewhat similar to the surface defect. What was the surface defect? The atoms at the surface of the crystalline material, they are less bonded. That's why they are more likely chance that they will react with the impurities. Same is the case here with the grain boundaries as well. The atoms at these grain boundaries, they are less bonded than compared to the atoms deep inside the grains. So the boundaries between these two grains is termed as a grain boundary. So atoms at these boundaries, they are less bonded compared to the atoms inside the grains. So that is the reason they are the high energy atoms. So they are in high energy state, they are less bonded, and they are more reactive compared to the atoms deep inside. And that is the reason when material is corroded, corrosion occurs along these grain boundaries. And even if we add impurity atoms in our structure, those impurity atom tends to flow towards the grain boundaries because there is a reactivity along the grain boundaries. Now moving towards the types of the grain boundaries. So grain boundaries has generically two different types, and there are not much science involved here. When the two adjacent grains have the high angle of misorientation, this is the angle of misorientation. If you draw, the atoms of this grain is arranged like this one, while the atoms of this grains are arranged in this way. So there is an angle of misorientation that is very high. So they are termed as a high angle grain boundary. While in these case, in the case of these two grains, we have an atoms arranged like this in this direction, while the atoms of the other one is arranged like this one. So the angle of misorientation is not that much great, or angle of misalignment. So they are termed as the small angle grain boundaries. Besides, there are some other characteristics of the grain boundaries itself. When we have a material that has large grains, so ultimately it has the lesser grain boundaries. Let's suppose this is a piece of an iron. It has large grains, right? It has 4 large grains. It has less grain boundaries compared to this piece of iron, which had the same volume, but it has fine grain structure. this one. Right, if you have a lot of small grains here, so it will have greater grain boundaries, large number of grain boundaries. So ultimately the interfacial energy or the reactivity of this material would be higher than the reactivity of this material. This material would be in high energy state compared to this material, so it will be more reactive compared to this one. Second thing, when a dislocation move, obviously this is a single grain, so it has a crystals in it in a same orientation. So let's suppose it has a dislocation here, a half plane edge dislocation, and that dislocation is moving towards right, and it keeps on moving towards right until a grain boundary arises. Now the atoms are no more arranged like this, instead atoms are arranged like this one. So dislocation has no way to move forward, right, because the orientation of atoms in next grain are creating a hurdle. They are acting as an obstacle, which we discussed in the beginning, that in the absence of obstacle dislocation can move easily, but when we have the obstacle like this grain boundary, dislocation cannot move, or at least it cannot move easily. So grain boundaries acts as a obstacle for the dislocation, for the plastic deformation as well. So that's why those material which have the fine grains, which have the small grain structure, they tends to be of higher strength than compared to the material which have the large grain or the coarse grain structure. So the iron with a small grain structure would have higher strength compared to the iron with the large grain structure. I hope it's clear now. And we can increase the size of the grain if we increase the temperature and allow it to cool it down slowly. So there are methods called the heat treatment techniques, which we'll study in this subject in chapter number 9, by which we can control the grain size. Depends upon our requirement. If you want a material to be malleable or ductile, we want a coarse grain structure. If you want that to be hard and with a high strength, we will make a fine grain structure. So we'll perform the heat treatment operations accordingly. Now there's another subtype of the grain boundary that is called a tilt grain boundary. So tilt grain boundary is nothing but a presence of multiple edge dislocation in the crystal structure. So that naturally causes the misorientation between the crystal structure. You can see here that naturally causes the misorientation between the crystal structure when you have the multiple edge dislocation. So we have the angle of misalignment here as well. This is called as a tilt grain boundary. There is a grain boundary, but it is somewhat tilted at certain angle. Now moving towards the third type, that was the twin boundary. Twin boundary is a special type of grain boundary across which there is a specific mirror lattice symmetry. So due to certain phenomena like the mechanical loading, or due to annealing, which is a heat treatment process we just briefly discussed in the last slide, because of that there is a certain symmetry creates in the crystal lattice, such that an atom on one side of the boundary has a mirror image on the other side of the boundary, like in the case of this atom. So atom here, and there's a twin boundary here which is acting like a mirror. So an atom is at the mirror image position on other side of the boundary as well. So that is why it is called as a twin boundary. It is creating twin of each atom. It is creating twin of each atom. The region between these atoms is termed as a twin, and it might produce due to mechanical shear or due to annealing, a heat treatment process. Twinning occurs on a definite crystallographic planes and in a specific direction. Both depend upon type of crystal. So twinning, like in the case of the slip, it doesn't occur in all the planes or the direction. It occurs on some definite crystallographic planes and specific direction, but these both depends upon type of crystal we are dealing with. So this was a brief discussion about the twin grain boundary. Now the last one is the miscellaneous defects, that includes the stacking fault. You must have studied the stacking sequence of FCC and HCP, the AB sequence and ABC sequence, right? So let's suppose if we have a ABC sequence, and in the layer, like in chapter number 3, and there's a layer in which B is missing. After A we have a C layer, so that is also called as a defect in the structure. If you don't remember it now, you just go through the chapter number 3. You will find the stacking sequence among the last topics of the chapter number 3, the stacking sequence of HCP and the FCC structure. Plus there's another phase boundary defect. Phase is somewhat similar to the grain, but it is a region in which not only the crystals are same, not only the orientation is same, but it also has the same physical or the chemical properties. So it means it has the same crystal structure as well. This is another condition in the phase defect. So in all the planar defects, in all the two-dimensional defects, there's one thing associated with every defect, that is the interfacial energy. That is energy at the surface, and the magnitude of which depends upon the boundary type. So the magnitude of the interfacial energy in each kind of the defect depends upon the boundary type. Either you are dealing with the twin boundary or the grain boundary or the external surface boundary, the magnitude of interfacial defect depends upon the type of the boundary we are dealing with. So this is the end of this lecture, and so we have discussed in this lecture the two major kinds of the defect. That was the one-dimensional, the linear defect, or which are also called as a dislocation. And in dislocation we discussed the phenomenon of slip, which is also a dislocation motion. And in dislocation we discussed two different kinds of dislocation, either edge or the screw dislocation. And then we move towards the third type of the defect, that was a planar defect or the two-dimensional defect. And in the planar defect we discussed the external surface defect, that the atom at the external surface, they are less bonded, so they are more readily react with the impurities. Then we discussed the grain boundary defect, that the region in the material which had the same crystal or the crystallographic orientation, that is termed as a grain, and there is some angle of misalignment between the two adjacent grains. So if it is greater, then we call that to be the high angle grain boundary. If it is smaller, we call that to be small or the low angle grain boundary. Then we discuss about the tilt and the twin grain boundary. So at the end of this lecture I will pass a question towards you, and you have to think about it and answer in the next lecture, in the next live session. That is, the surface energy of a single crystal depends upon crystallographic orientation. The surface energy of a single crystal depends upon crystallographic orientation. Does this energy increases or decreases with the planar density? Right? So if a crystallographic orientation, the surface energy of a single crystal of a certain plane in the single crystal, does it increases or decreases with the planar density to the density of the plane? So and it is associated with what we have discussed in this lecture. So you should think about it and answer me, not just in yes or no, answer me with why is that so. Thank you for your time. I hope we will meet in the next lecture. Assalamu alaikum warahmatullah.